Thank you for the nice welcome. As I said, my name is Stefan ten Bolen. I studied at the Technical University of Aachen, worked then for a while, for some years, at Alstom, and was there responsible for the electrical and mechanical design of power transformers. In 2004, I'm with the University of Stuttgart. Today I will talk a bit about the design requirements for optimized condition assessment of power transformers. And in the beginning I want to talk a little bit about the reason why transformers fail, and then I want to introduce you to the partial discharge measurement and condition assessment by this technology and online monitorings. And of course the main topic, what requirements has to be foreseen at the transformer to do these measuring technologies. First of all, why do we need condition assessment? I have here two examples. Left-hand side, it is a fire on the generator step-up unit of a nuclear power station in Germany. Yeah, so this happened 3 months before the elections here in Germany, and you can imagine that smoke in front of a nuclear power station here in Germany had a tremendous effect. So it was a high topic during the election campaigns of several parties. So besides, let's say, the technical and economic effects, there was also a big effect on the political discussion of this. So such a failure, of course, should be prevented. But utilities are, of course, facing a cost pressure. They have fully to utilize the capacities and lifetime of their equipment. The specialized personnel is reduced, and also maintenance strategies are revised. Problem is, first, you can save money with that, but eventually the failure rate might be increased. And this, of course, generates a lot of costs, these failures we have seen in the former slide. So how to prevent this? You need reliable diagnostic to really have a reliable condition assessment of the equipment. Within SIGRE, I'm the convener of a working group which collects information about major failures. We initiated a survey where 55 utilities from 20 different countries participated. In total, we investigated a population of almost 30,000 transformers, and we collected the failures which happened, let's say, during the last 10 years. So we achieved a quite good response to this survey, and if you start to calculate then the failure rate of power transformers, you can see for substation transformers we are in the range of 0.41%, which means if you have 100 transformers in your population, then 0.4 will fail within 1 year. So let's say if you have 250 transformers in your population, you can expect with one major failure. This is in fact not a very high failure rate, so a transformer failure is a quite seldom event, but as we've seen in the pictures, it's also a costly, very costly event. Therefore, of course, it makes sense to prevent that. And in order to prevent that, you have, of course, to check what are the causes of such a failure. And so we analyzed the major failures according to the failure location. And in these statistics, you can see that, let's say, more or less half of the failures are attributed to failures within the winding insulation. So between windings, within the winding, also lead exits. So this means the internal insulation system. But also bushings and tap changes are reason for failures. In elder surveys, the tap changer was more often a reason for major failures. This is reduced because there is the use of new materials, better maintenance strategies for tap changes. So this number is decreased in this recent statistic. Let's come to the part partial discharge measurement. What is partial discharge measurement? What different type of technologies are possible there? And what are the things which you need at the transformer to do such a partial discharge measurement? Before I start with this topic, I have to give some definitions because I'm using these words and often it is not absolutely clear what these words mean. The first two is off-site and on-site, and of course these words are relating to the place where the measurement is done. Off-site is in factory. For example, the acceptance tests after manufacturing the transformers are normally done in the test field of the factory, so these are off-site measurements. On-site means the measurement is done in the substation or in the power station. And this means, of course, a big difference, because if you are going on-site and measure there, you are not in the shielded environment of a test field, therefore you have bigger noises, and therefore you have to adapt your measuring technology to these circumstances you have at an on-site measurement. So second, we have to distinguish between offline and online. Offline means that the equipment under test is disconnected from the power grid, and online means the equipment under test is connected with the power grid. Both methods have its advantages and disadvantages. So if you do an offline measurement, you have the advantage that you can control the voltage, but disadvantage, you need a generator to generate the test voltage, for example. So normally an offline measurement needs much more expenditures as the online measurement. The online, in turn, has the advantage that the voltage is already there because the equipment is connected to the grid. So you really test it under real conditions. It's an advantage, but unfortunately also noises which you have, of course, on the grid voltage are influencing your measurement. The third is online monitoring. So we have to distinguish here between an online measurement, which is a measurement done just on one day, so a single event, and online monitoring means you have a continuous acquisition of measuring data during the operation, and probably also automatic assessment of the data. So this goes one step beyond the normal online diagnostics, where you measure and then you look at the measuring data and you interpret these data by specialized personnel. The monitoring system should do this continuously, so it should work quite reliable, and furthermore it should work on its own. Yeah? So there is no engineer in front of the computer to adjust the monitoring system. It should work on its own, and it should say what is the condition of the transformer. So you need quite good modeling of the failure behavior of the power transformer. So let's come back to the PD measurement. In this graph I show the, let's say, the equivalent circuit of a conventional PD measurement according to IEC 270. Let's say you have here your transformer. The insulation system of the active part is shown here as a capacitor A, which is connected via the bushing to a generator, to a voltage generator. This can be, in case of an offline measurement, a separate voltage generator, or this can also be, in a case of an online measurement, the electrical grid. So once you have partial discharges in the insulation system, partial discharge is a partial flashover in the localized on one spot in the winding, so you do not have, let's say, a big arc inside the transformer, but more or less little sparks. So, and you can measure these sparks by connecting, let's say, this measuring circuit, which consists of the bushing capacitance and a quadrupole. In order to connect the quadrupole, you need a measuring tab at the bushing. This is shown here in this picture. Yeah, so we have here the high voltage bushing. Here is a measuring tab, and at this measuring tab there's a connection of a quadrupole. And with this quadrupole you can decouple the high frequent partial discharge impulses which are flowing in this circle here, and you can acquire them by digital electronics which stores all partial discharges. And it integrates the current impulse, and by the integration of the current pulse you achieve the charge of it. And this is shown in the diagram, the result. So you have here on the x-axis the phase angle of the applied voltage. Yeah, so here 0 degrees, here 360 degrees. You can see here the applied voltage. And in case here of these offline measurements, you have not the perfect clear 50 Hertz. You have also resonances on this voltage, which results here in this buckling of the sinusoidal curve. So now the partial discharges are put into this diagram according when it was originated, so at which phase angle. So let's pick maybe here one little blue point, which was acquired at, let's say, 90 degrees phase angle, and on the y-axis you have the amount of charge within this impulse. So, and you do this measurement for a certain time, let's say 10 minutes, so acquire all partial discharges within 10 minutes and put it here in this diagram, and then you can see by this color how often such a partial discharge occurred. Yeah? And so then you can see these type of patterns, which are called phased resolved partial discharge patterns. These patterns can be analyzed, and from the analysis of these patterns you can draw conclusions what are the problems within the insulation system. The problem with this technology is that during on-site measurements you have quite a high noise level. Yeah? So also disturbances here on the network are shown in this graph, and maybe they hide the internal partial discharges. This conventional PD measurement is standardized, and it is of course also used during the acceptance tests of the power transformer, but as I said, for on-site measurements you have to develop this technology a little bit more. And in order to measure free of noises, two other technologies were developed. One is the acoustic PD measurement. With the acoustic PD measurement you connect microphones to the transformer tank wall, and you measure more or less the acoustic emissions from the PD by these sensors. And therefore you have no problems with the noises which you have on the transmission line, because you simply do not detect them. You detect with this only internal partial discharges. Okay, but also this technology has its disadvantages. One disadvantage is that inside the active part there are a lot of components. We can see these components here on the fair, and therefore you have also a strong damping of the acoustic signal from on its way from the source to the microphone. So problematic is the high attenuation of the signals. One benefit of acoustic measurements is that by measuring the time which the acoustic signal needs from PD to the microphone, you can do a localization of the partial discharge. For this you have to install several microphones on the transformer tank, and then by solving these equations you can localize the PD. I will show you later one example where this was done. Second unconventional method is the UHF PD measurement method. Principle behind it is that you bring an antenna inside the tank wall and you measure the radiomagnetic emissions of the partial discharge. So you measure in a very with a very high bandwidth in the gigahertz range. And in this high bandwidth, let's say the transformer tank acts as a Faraday cage. So the noises externally of the transformer cannot pass this transformer tank wall, and therefore if you measure with this antenna a signal, then it must be generated within the tank wall. So you have a good possibility to distinguish between internal and external partial discharges. Furthermore, you can use this signal because it is very sensitive for PDs. You can use this signal for triggering the acoustic signal. Yeah? So you connect this antenna to the trigger input of your oscilloscope. The measuring channels are connected to your microphones, and once you receive a signal from the sensor, you measure also the output of the microphones. This is shown in this slide. So once trigger, you measure this output signal from the acoustic sensors. And if you now look at this signal, you would say, okay, this is simply noise. What can I read from this signal? But if you go and you measure a lot of these acoustic signals, and you are calculating an average signal, you can decrease the noise level, yeah? Because the noise is of course statistically distributed, and if you build an average, you decrease the noise. And this can be shown here in the video, which I show here. So we accumulated here 20, 30 and more of these signals, and the more you have, the lower the noise level is. And after a while, the real acoustic response from the microphones are coming out of the noise. So we have here now more than 100 signals averaged, and now you can see here this was a UHF trigger signal, so the acoustic wave needed this time until it arrived to the sensor. And this is now the time, sorry, this is now the flight time of the signal. And you have to use this time flight, of course, in order to find the local, the spot where the partial discharge occurs. How is such a UHF sensor looking like? There are two types. This is a drain valve sensor. You can connect this sensor to an oil drain valve. You normally have at a transformer several of these valves, at least one, in order to remove the oil from the transformer tank. So you can connect here this probe, then you open the valve, and then you can push the antenna inside the transformer tank. This is a sensor for standardized DN50 and DN80 valves. So let's say from the design perspective of the transformer, you have to foresee such a valve. Okay, this valve must have, of course, a direct throughput, yeah, as shown here for these three types: gate valve, guillotine valves, and ball type valves. These are useful, but of course there are also other type of valves, so globe valves, butterflies, or diaphragm valves are not possible to be used with these UHF sensors. Yeah? So during the design process, you should take care that these three types of valves should be used. If you are building a new transformer, also directly during the manufacturing process, these UHF plate sensors can be installed. Yeah? Here is a drawing of such a plate sensor. You have here the antenna, and you have here some plastics which prevents that the oil comes out of the transformer, so it's more or less a dielectric window, and into this hole you put the antenna, and here you can see the full installation. The advantage is you can install quite easily at several locations UHF sensors, and thus it is possible to increase the sensitivity of the measurement. I want to present you an example of this measurement. In this case, we have a single-phase auto-transformer, 380 kV. It was constructed 1966, so quite an old transformer. And the oil analysis of this transformer revealed a high hydrogen content, and so partial discharges were expected. So we installed then 3 UHF sensors, because there were 3 valves, one on the bottom of the tank and 2 here at the top of the tank. You can see here the pictures of the installation of the UHF sensors. Then the transformer was again connected to the grid, so it was an online measurement, and you could measure on all 3 UHF sensors these signals which show a partial discharge. It was also possible to develop such a PRPD pattern based on the UHF measurement, and here, for example, is the frequency content of the UHF signals, and you can see you have here signals up to a frequency of 1.5 gigahertz. So, but now, of course, we detected the PD. Now it's a good question, where is the PD and is it critical? So we installed additionally microphones here on the transformer tank, and then we measured the averaged signals. So we triggered on the UHF signal and averaged the acoustic signals. This was the result of such an averaged signal. It does not look so pretty nice as the signal before, so it's also not so easy if you have this signal to say, no, okay, this is exactly the arrival time, or is it here at the peak, whatever. To determine this arrival time, we are using a so-called Hinckley criterion, which is based on the energy content. Yeah? And don't know if you could see here this green curve. Yeah? It has its minimum here, and this means that exactly at this time is the arrival time. So we had the arrival times of several microphones, and so we could localize the PD, let's say, near of the tap changer. So, and you know, the tap changer is accessible if you open the transformer, so it was decided to bring back this transformer to the factory. The active part was open, and these are some pictures from the tap changer, and you couldn't see here these black spots on the connections on the tap changer lead exits. And for sure, if this transformer would be kept in operation, this partial discharge would have developed, and you would have a flashover here between the tap windings. And normally such a flashover within the tap windings means destroy of the full winding, because the currents are too high for the tap winding, and that would have been resulted in a major failure. And so it was possible to repair this transformer just by exchanging here the paper and cleaning everything, and now the transformer is put into operation and is PD free. This was an on-site measurement, but it was not on-site monitoring. Here in this figure, I show you the result of an UHF PD monitoring system. So for a longer time interval, the PIPD patterns are stored, and you can see that these PIPD patterns are changing quite a lot during the time. So here are 3 days are shown. So during the 3 days, you have strong changes in the PIPD pattern. So PD is not a continuous process. PD can also develop. And now is, of course, the question, what does this mean? We have here, let's say, established new pattern recognition technologies, because you are acquiring a lot of data and you have to analyze this data automatically. At certain time intervals you get, for example, these PIPD patterns. At other time intervals you have these patterns, and you can see here you have this one here, this so-called finger in your pattern. Here you do not have these fingers, so you can see that there are partial discharges which are only active for certain time intervals. So let's say currently we are working on really on the interpretation of all these data, but you can see here that PD monitoring is problematic, not because of the measurement technology, this we have developed quite reliable, but because the interpretation of the data. But of course, interpretation of the data you can only learn from data which you have measured, so I think it will need some more systems and years to gain the experience really to interpret these signatures reliably. In the second part, I want to talk a little bit about online monitorings. Online monitorings means that I do not only use such a PD measurement in a monitoring system, but let's say the full scope of a transformer I'm monitoring. So bushings, step changers, active parts, by measuring a lot of quantities. The idea behind is that if I do a continuous supervision of several quantities, I can do exact statements about the operating condition. For example, by measuring of the temperatures, I can make statements about the current overload capacity of a transformer. Furthermore, of course, I can early detect incipient faults, and that is the reason that I can transfer then from the time-based to a condition-based maintenance, and of course by the knowledge of the transformer life. So this knowledge is recorded by the monitoring. I can estimate the remaining lifetime. So first I want to show what are we doing in the case of the bushings. We have here such a bushing. The high voltage bushing is normally a condenser bushing, which means inside the insulation system of the bushing you have different layers, metallic layers, and the last layer is connected to the measuring tab of the bushing. I showed this measuring tab already for the PD measurement, where I use this measuring tab for PD measurement, but I can also measure the voltage which is applied to this bushing. Here you can see such a voltage sensor, so you have here a connector to the measuring tab, a cable to the voltage sensor. Okay, now the question, what is the voltage sensor? You can see that here. You have the bushing capacity C1, and then you connect here this voltage sensor, and in this voltage sensor you have a second capacitor, and both capacitance means you have a voltage divider. So, and the output voltage of this voltage divider is of course dependent on the grid voltage, but secondly, of course, also on this capacitance C1. And in case you have a partial flashover here inside this bushing, then this capacitance C1 is changing. This does not mean a major failure, but of course this partial flashover within 2 layers can develop in a complete flashover of the bushing. So once you detect a change of this capacitance by measuring here the output voltage, you have to exchange the bushing. An example for this is shown here. So we can see here the voltage from the 3 phases, and here at this event the voltage of one of these phases was a little bit increased. Not very much, so we have here, let's say, 430 kV, and here we have 440 kV. So it's not a tremendous increase, and for sure this would not trigger any alarm. But if you calculate from these voltages the change of capacitance, you can see here this increase of capacitance, roughly 3.6%. And if you go into the design of such a 420 kV bushing, you can see you have roughly 40 layers, which means if one layer is short-circuited, you have a change in the capacitance of 2.5%. So this change of 3.6% means that there's roughly a flashover of 2 layers. This bushing was then exchanged and it was investigated, and indeed it was this flashover inside the bushing was found, and for sure if this bushing would have been kept longer in operation, this problem would have been developed into a full flashover of the bushing with explosion and fire and all these bad results of a major failure. Let's come to the active part. In the active part you measure load current and oil temperatures. These are the most important measuring quantities. Oil temperatures you can measure by a PT 100, which is installed in a so-called thermometer pocket. For the design of the transformer, it means foresee 1 or 2 thermometer pockets in case you want to install an online monitoring system. So load current is measured by current transformers in the bushing turrets, and often these current transformers, or normally these current transformers, are used for measuring the nominal current and short circuit currents. If you want to use this current transformer also for monitoring, you have to foresee, let's say, one of these current transformers, because during manufacturing or during the design process it is quite cheap to foresee such a current transformer, but later if the transformer is installed in the substation it's almost impossible to exchange or to add one current transformer in the bushing turrets. By measuring of ambient and top oil temperature, you have the ability to, by use of a thermal model of the transformer, to calculate the maximum overload capacity. This is done here in this case. So you can see here in blue the ambient temperature curve, and this was time interval during November, and you see the outside the ambient temperature was between 0 and 10 degrees, which is quite low, and because of this lower ambient temperature you can overload the transformer, because of course the cooling unit is working more efficiently, and you can see that here in the black curve, because this shows the maximum overload capacity, and you can see that most of the time you had an overload capacity of 1.3 possible with this transformer. This is especially maybe a solution for the wind farm transformers, because these transformers are fully loaded, especially at times where you have strong wind. Strong wind in turn means good cooling of the transformer, so then at these times you can really also overload the transformer, and by means of such a monitoring system you can calculate this. One important sensor is such a gas in oil sensor, because as I said before, if you have problems in the insulation system, for example, hydrogen is generated, this hydrogen can be measured continuously with such a sensor. There are also systems which measure a lot of other gases. I present here just, let's say, the single gas measurement by an example. So you have here a time interval of several months, and on the y-axis you see the hydrogen content. And you can see here a step-like increase of this hydrogen content, and it was found that always in one tap position there was a strong increase of hydrogen content. It was there at a quite high level of almost 500 ppm, and then the utility, or in this case it was an industrial industry transformer, an oven transformer for a steel plant. It was decided to install an oil treatment which degasses the oil. So the gas is removed from the oil, but of course the cause of the gassing is not removed. And on one day there was here a quite strong increase, and it was led to a really flashover inside the transformer. So there was full loss of the transformer, also loss of the electrical energy which was used for the oven, so there were a lot of collateral damage in the oven. The reason was, at this point we gave an alarm, so we sent a fax message to the utility and said you have to do something, but this was on Friday at lunchtime. And you know what is happening with a fax which you receive Friday at lunchtime. This should have time to wait until Monday. But unfortunately on Saturday the transformer said, no, it's not, it's now a good time for me to pass away. So if you install such a monitoring system, you also have to believe and to react on the indications of the system. In this slide you can see a lot of measuring quantities which are able to be installed. Because of that, the CGRE initiated a working group which evaluated all these different sensors, and it came out with a table where all the different sensors are shown, and dependent on the level of monitoring there is a recommendation to fit something or to leave it out, or just to foresee a facility of it. So for example, top oil temperature is a quite cheap measuring quantity because it needs just a PT100. Such a PT100 should always be foreseen for a monitoring system. Such a multiple gas monitor, I showed just single gas monitor. Such a multiple gas monitor, you should just foresee the facility to install something like that. So and you can see for cooling unit, bushing and tap changer, there are different sensors which can be installed there. These sensors deliver their signals to a monitoring cubicle. So you have here normally standardized output signals, so 4 to 20 milliamps output. These signals are digitized here in this cubicle and then sent by a field bus to a computer which stores these data, which assess the value of the data, and gives also alarms. This is the inner side of such a cubicle. So you have here these bus terminals for to digitize the signals, and you have then here just one field bus cable. In this case, the PC is installed also in the cubicle, so not in a room in the substation. Modern industrial PCs are really be able to be installed in such a cubicle, which is installed here directly at the tank wall of the transformer. This server can then communicate with the protection and control system by means of digital protocols, for example, the new IEC 61850 protocol, or in former times, if there was not such a good a communication link also via modem and telephone line, but also, of course, with TCP/IP, with the intranet and the internet. This is, for example, here it is shown how it is used within a big utility. So you have in the power station or in the substations these monitoring servers. They are connected to the intranet of the utility, and the operation department, the asset management department, or the maintenance department have access to the data of the transformer, maybe not only the transformer, but also circuit breakers and so on, and can then derive their actions based on the result of the monitoring system. That is the HMI, so the visualization of the monitoring data. This can be done, for example, with a web browser, so you do not need a dedicated software on your PC. You can just use your normal web browser. So I come to the conclusion. Cost pressure requires condition assessment in order to adjust the maintenance strategies of a utility. The sensor technology is rapidly developing, but parameters and basic sensors not likely to change so much. So facilities can be provided at the transformer also for future sensors, and a standardization would be helpful. In the meanwhile, some parts are standardized, but if you need more information about that, I can recommend this SIGRE brochure. If you are a member of the SIGRE, you can download it for free, otherwise you have to buy it. And in this brochure, there are the recommendations for condition monitoring described. So thank you very much for your attention, and in case of questions, don't hesitate to ask. Thanks.